There's this incredible idea, almost science fiction. A car that never needs a gas station, never even needs to be plugged in. It just sits in the sun, generating its own fuel. It's a powerful, alluring concept, for sure.
But that raises the big question, right? If this idea is so amazing, why aren't our driveways full of them? To figure that out, we have to push past the dream and get right into the hard science that actually governs this whole thing. Okay, so let's break it down to first principles. A solar car is really just a direct energy system. It lives and dies by one very simple but very strict equation. The energy you get from the sun has to equal the electrical energy you use, minus all the losses along the way. Every single step, from a photon hitting the roof to the wheels turning, is controlled by this fundamental energy balance.
And is that simple balance that creates the collision course between the dream and, well, reality. Because the biggest challenge here isn't the lack of technology, it's the hard, unchangeable limits that physics itself puts on the table.
Yeah, the dream basically runs headfirst into three physical brick walls. First, there's the solar flux limit. The sun only sends so much energy our way, about 1 kilowatt per square meter. That's our entire energy budget, period. Second, the Shockley-Queisser limit. This is a fundamental rule for silicon that says even a 100% perfect solar cell can only turn about a third of that sunlight into electricity. And finally, you have the area constraint. A car just isn't that big. These three things together create a really formidable barrier.
What you end up with is something you could call a power funnel. You start with this huge flood of energy from the sun, but right away the car's small surface area cuts that down. Then the physical limits of the solar cells themselves take out another massive chunk. By the time you get to the end of the funnel, what's left is just a tiny trickle of the energy you started with.
So here's the number that really matters. After all those physical limits take their cuts, a typical solar car, on a perfect sunny day mind you, can generate a maximum of about 1.5 kilowatts. That's 1,500 watts, okay? Remember that number. That's our total supply.
Now, let's look at the other side of the equation, the demand. A regular electric car needs somewhere between 10 to 20 kilowatts, that's 10,000 to 20,000 watts, just to cruise at highway speeds. You can see the problem, right? The supply and demand aren't even in the same zip code.
This huge gap creates what we can call the great power mismatch. The sun is only giving you maybe 10% of the power you actually need to drive normally. This single problem, this energy density problem, is the one challenge that defines every single design choice in a solar vehicle.
So what do you do if you can't change the laws of physics? You can't. So you have to get incredibly clever. And this is where the engineers step in, trying to fight back against physics with some truly radical ingenuity.
To even begin to bridge this power gap, engineers use a 5-part system where every single piece is obsessed with efficiency. You start with the absolute best solar arrays you can get. Then you pair them with a maximum power point tracker to squeeze every last watt out. A super lightweight battery stores the energy, and high-efficiency hub motors get power right to the wheels, cutting out any waste. But honestly, the most important part is the 5th one.
The aerodynamic body. And the reason this is so critical comes down to some brutal physics. The power you need to push air out of the way goes up with the cube of your speed. That means if you double your speed, you don't need double the power, you need 8 times the power. It's an unforgiving law, and it's why these cars look like something out of a sci-fi movie. They are literally sculpted by that equation.
And this is what you get when you push that principle to its absolute extreme. The Nuna 2 is basically a scientific benchmark. It's so light, so aerodynamic that it only needs about 1,650 watts to go 100 kilometers per hour. Now think about that. That's incredibly close to the 1,500 watts the sun can actually give you. This is engineering getting as close as humanly possible to actually closing that huge power gap.
So how does a solar car really stack up in the real world? Well, if we compare the systems, a gasoline car is practical, sure, but its engine is only about 25% efficient. A normal EV is way better, super efficient, around 85 to 90%. A pure solar car's efficiency from sunlight to motion is actually kind of similar to a gas car's, but its practicality is, well, it's extremely limited. It's an absolute engineering marvel, but you're not taking it to pick up groceries.
And that really gets at the core difference between a scientific experiment and a car you might actually buy. On the left, you've got the scientific extreme, the Nuna 2. On the right, a practical application, the Aptera. See, to make a vehicle for the real world, you have to make compromises for things like safety and carrying stuff and comfort. And every one of those compromises pulls you just a little bit away from that razor's edge of pure efficiency.
Realizing this leads to a huge shift in thinking. Maybe the goal isn't a car that runs entirely on the sun. Maybe the goal is something far more achievable, and honestly, maybe a lot more useful: the solar-assisted EV.
The Aptera is the perfect example here. Because it's so ridiculously efficient to begin with, its solar panels can add up to 40 miles of range a day. Now, for the average American driver, that covers their entire daily commute. It's not running only on solar, no, but the solar is so effective that you might almost never have to plug it in. This is proof that solar as an assist mechanism is incredibly viable.
So this is the big paradigm shift. We have to accept that a fully solar-powered car for the mass market just runs into a wall of physics. The realistic, and I think much more exciting future, is using solar as a constant free energy top-up for a hyper-efficient EV.
And the science is definitely not standing still. People are doing incredible research into next-gen multi-junction cells that can actually break that old Shockley quasar limit. There are concepts like solar paint, new ultralight materials. All of these things are continuing to chip away at the problem from both the supply and the demand side.
Which brings us to our final scientific synthesis of all this. A solar car, in the modern practical sense, is really just a super optimized, incredibly energy-efficient EV that uses sunlight as a bonus, a supplementary power source to stretch its range and rely less on the grid.
So let's just be crystal clear about what this tech will and will not do. Solar will absolutely assist EVs. It will dramatically reduce how often you have to plug in, and it will increase the total efficiency of the system. What it will not do is completely replace plug-in charging for a normal, heavy, inefficient car. The physics just won't let it.
So when you look at all the science, it turns out we've been asking the wrong question all along. The question isn't when are we going to have solar cars? The much better, more relevant question is, how soon will my car be solar assisted? And based on the engineering that's happening right now, the answer to that is probably a lot sooner than you think.